Hi everybody, I'm Nader Sadubi. I'm here from the University of Texas at Austin today. I'm a student, and I'm very excited to share with you all my presentation about my paper, Translating Albers to CAM16, a case for next generation color pickers. So first, the story starts in 2016, before I even was in college, and I was just a little high school student. This is Agora, the coffee shop I would go to every day after school, and that's when I first started reading Albers' Interaction of Color. I wanted to follow along with his examples, so I would use the color picker and illustrator to just try and, he said, keep them the same lightness. I tried to make them the same lightness, and it didn't really work, and I was kind of mad. Later, when I was in school, I was actually assigned the book as a textbook to do for my classes and read and study and replicate his own exercises. But I found that when I actually use color appearance models and other more perceptually relevant tools, that I was able to do his assignments with the bullseye every time automatically. In high school, when I was trying to do this in Adobe Illustrator, I was using a tool known as HSB, which was distorting the color relationships that Albers speaks of, because Albers was talking about perception. He had only his eyes. This was back in the 60s. But CAM16, because it's perceptually relevant, did not distort Albers' assertions, and I was actually able to replicate what he was doing with the system. And so this slideshow is going to talk about vibrating boundaries and show them, and they're not going to show on this projector. So if you could get out your phones, you have this QR code over here. If you scan it, it'll load the web page where you'll have some sRGB calibrated previews on your mobile device. And I'll give you all a second. All right, so the first example of a vibrating boundary will be Albers's. Yeah, this one's a vibrating boundary. This one's from plate Roman numeral 22-2. And as you can see on your mobile devices, they're glowing. And these colors, if I were to take that pink and put on a white background, it wouldn't glow like that. They're glowing because they're like that with each other. A vanishing boundary is a similar effect, but they vanish. They don't glow. It's pretty self-explanatory. And so, in the middle, you can see HSB trying to perform Albers' instructions on a vibrating boundary and not vibrating. You'll see this better on your phone, and on the right, you would on your phone see CAM16 actually get the job done. So a little bit about Albers' instructions of what a vibrating boundary actually is. He states that a vibrating boundary is between colors which are contrasting in their hues, but also close or similar in light intensity. And so what is light intensity? Albers gives us a clue in his text where he actually equates it directly to Munsell's value. And as we understand that Munsell's value is really talking about what the CIA calls lightness, we can see that Albers' light intensity is really what we would call lightness today. And so going back to his recipe, we can simplify it into requiring two ingredients. One, the hue's got to contrast, and two, the lightness has got to be equal. Vanishing boundaries, he goes on to explain, are essentially the same, just with similar hues instead of contrasting hues. And so this lightness equality is the problem with these vibrating and vanishing boundaries. Albers himself says that this is a challenging exercise, a most difficult task demanding most of all patience. That sounds hard. And he even goes as far to say that it may appear hopeless to find equal light intensities in paint and painting, colored papers, in our surroundings, and I'll add in 2024 and HSB in your Photoshop color picker. And so why are we testing vibrating boundaries though? Why does this matter? So because vibrating boundaries are such an exaggerated scenario, the lightnesses must be the exact same for them to vibrate. If they're different, they won't vibrate. It gives us an exaggerated clarity of insights relating to HSB's defects. Its main defect being, it doesn't show lightness correctly. On your phone, you'd see HSB's attempt at what would be a vibrating boundary, according to his color picker. These should vibrate. These follow Albers' recipe. But on the right, you'd see on your phone what an actual vibrating boundary of that blue background would be and of that yellow background. The reason why HSB does such a bad job of doing vibrating boundaries is because it shoves our human color perception into unnatural squares. On the right, you see the sRGB gamut is going around with CAM16. Meanwhile, on the left and right, you're seeing those same hue slices in HSB and HSL. And we're getting this irregular shape. Like, you can have like really bright, vivid yellows, but there's no such thing as this color system, an sRGB display being able to produce like a vivid, bright blue. And so you're getting this shape that changes with every hue, and we're just shoving it into a cylinder. And this doesn't work out. And so when you keep the saturation, the brightness is the same, which according to Albers is requiring equal lightness, which that may not be lightness, but in the color picker, that's the closest thing to lightness you have when you're an illustrator. And so by keeping this brightness attribute the same, as we're going across the hues, we're actually changing perceived lightness, as you can see in this graph, showing how in CAM16 the lightness has changed. And so to look at Albers' claim and analyzing it, to look at Albers' claim and see how we'd analyze it, we would first actually scan some of his illustrations. So Albers has 6 examples of vibrating and vanishing boundaries, 3 vibrating, 3 vanishing. I had to omit from study the first vibrating example because it had a thin radius of lines that my spectrophotometer couldn't measure. And so the measurements were taken from a pristine copy held at the Harry Ransom Center. Acknowledgements to the Alfred Knopf Library for their generosity in donating the specimen. And the measurement tool used was a NIC Spectro L spectrophotometer. I underlined photometer because it looks like a spectrocalorimeter. It's really slim, but it's actually giving me raw spectral data from that. And I measured in M2 measurement mode. I didn't put it on here. And color conversions were done in Color Science for Python version 0.44, the alpha. And so all the calculations from the spectral data to XYZ to RGB, LAB, CAM02, CAM16, and from RGB, HSB, B, and L were made. That way we could take out these green variables and evaluate just those lightnesses. And so delta L is a number we're going to talk about for the next couple slides, and it's the lightness difference. So you have a background color and a foreground color. Albers says they're supposed to be the same lightness. So if I want to evaluate if a color system's lightness metric is actually corresponding to Albers' claim of equivalent lightness, I'd want to figure out how far apart the system thinks they are. And so with this delta L, taking the first number and subtracting it from the second one, we get just like a whole number. Well, not a whole number, but we get a number, delta L. This one, in this case, it's 2.1. And so understanding these delta L values, like what is a good value and what is a bad one, we see that since Albers' claim was of equivalent lightness, that would mean that delta L would have to be 0 to match Albers' claim. So 0 is a perfect agreement with Albers. The lower the number is, the better that system is performing. The higher the number, the worse it's performing. Just remember that. High numbers are bad, low numbers are good. When we evaluate the color systems across the board, looking at the green ones being their best performing cases, the orange ones being their absolute worst performing cases, and yellow being average, we see something pretty cool happening. So HSB and HSL obviously do not make the cut. They horribly describe lightness, which is why you have something that Albers made to vibrate. HSL saying they're 35 lightness units apart, and HSB saying 12 lightness units apart. But the interesting thing to notice here is that HSB and HSL actually never perform as good as CAM16 or even CAM2. If you can see, their lowest value is still higher, so their best values are higher than CAM16 at its absolute worst. And so we can already tell that HSB and HSL just do not correspond to Albers as well as CAM16 does. But when we actually do some t-tests, the t-test done in this case was a set of paired one-tailed t-tests with each system to exist as a column of zeros. With p-value 0.01 being our statistically significant threshold, we find that CAM16 was the only example that actually was statistically significantly corresponding with Albers' claim of equivalent lightness. And so when we do the reverse engineering and look at, okay, let's measure what his folios are saying, we see that CAMs are corresponding with Albers' claims. But now in terms of actually applying them, we can see that, going back to the recipe, contrast hue equal lightness. We numerically express that by just taking the first hue, adding 180, keeping the lightnesses the same, and having the chroma be whatever the maximum chroma is possible in the sRGB gamut. And so this one you're going to want to see on your phones. It's not going to vibrate up here. But you see HSB and HSL fail in every scenario. CAM16 does a pretty good job across the board. And CIA Lab does okay too sometimes, but there's some, this one's hidden in this slide, but on your phone it'll show. The problematic blue region exaggerates some hue differences, and so you have that weird green color showing as its complement, when really blue is opposite yellow. And so this is the reason why HSB was doing so bad. We can see this is what I was talking about in those early slides, when I was saying that the color picker was distorting Albers' relationship. But with the perceptual color picker that actually matches the way I, the human, seeing this thing, making this art, sees, it doesn't distort the relationship. I can actually follow along with my tool what Albers was writing in 1964. And so this, in a sense, actually redefines some artistic limits. Remember how Albers was saying this is a most difficult task demanding most of all patience? So I was able to do it in Python in 2 milliseconds. No, for real, watch. Let me run it. You'll see. It actually has a runtime of 0.0014 seconds, which I had to Google, and 0.001 is a millisecond. So this really difficult task that Albers says takes forever is actually doable in CAM16 in Python in 2 milliseconds. So imagine what would happen if we actually had this color picker on the market. And so these ones will definitely not vibrate on the screen, but you'll see them on your phones. We're now able to even have novel techniques such as the vibrating gradient, is what I call it. Because Albers was limited to 2 vibrating colors to form just boundaries because it was such a difficult and labor-intensive task. But with like CAM16 and Python automating things for me, I'm able to put hundreds of interchangeably vibrating colors together at gradients. But vibrating boundaries are essentially useless though. They're non-accessible, you can't see them, why are we studying this? So, vibrating boundaries, remembering that there is a really exaggerated lightness use case, we see that there's some other lightness critical use cases that are actually incredibly important. If CAM16 were a color picker being used by a graphic designer, you wouldn't need no extra accessibility color checker, because actual lightness, actual perceived lightness would be baked into the tool. You just throw up lines to see what the thresholds would be, and you would just pick a color that fits, as opposed to having to switch your windows back and forth. Designers in the audience will know. And so we just come down to one choice at the very end of all this. Are we going to continue to try and fit a square peg into the round hole that is our human perception? Or are we going to actually decide to give designers tools that match the eyes and brains they actually have? I think we should do that. Thank you.
Any or question? Actually, I have some comment because I'm familiar with the CAM19. If you want to use CAM, CAM stands for color appearance model.
Yes.
It wants to deal with illuminant adaptation and also chromaticity adaptation and simultaneous contrast. But it needs more parameter. It means you need adaptive luminance and background luminance and so on to have the accurate calculation. But normally, if you use mobile phone, we cannot accumulate.
So actually, I can answer.
Kind of parameter.
Yeah, so I can answer that question for you. So a part of what I had to do from the get-go was I had to find what are going to be some parameters to keep constant. For the audience that isn't really familiar with these parameters, CAM16 like calculates how we would perceive a color based off of like some very specific parameters, like what's the adapting field luminance? Is the viewer discounting the luminance or not? What's the light point? This and that. And so there are a lot of very, very specific things that you have to actually measure the environment in order to even have a meaningful CAM16 reading. If you don't have those parameters, you don't have a CAM16 reading. You can't calculate it. But there's actually, it was when I was looking at the color science for Python package, it was in the CAM16 UCS page in the documentation that I noticed that CAM16 UCS actually uses a set of static parameters. It was 80 candles per square meters for adapting luminance. I think it like was discounted. I have the specifics in my paper of what the parameters were. But by having just one set of parameters that you keep constant, even though yes, these aren't meaningful CAM16 readings that are valuable to the color scientist, for the artist that just wants a better color picker, it's better than this. This is what we have right now. If we just have some static parameters, we can take advantage of like the revisions that have been made, as opposed to, let's say, CIE Lab, that I have the slide hidden here. CIE Lab has, that blue region is a problem. I may be able to find it, and if not,
Yeah, LAB space, the blue luminosity is very poor.
The uniformity sucks. It goes from blue to purple, like to white. It's bad. And this is, for like artists and designers, like they need a color picker that works. We need a color picker that works.
Yeah, so if we have a simplified CAM16, will be much better. Do you agree that?
To simplify CAM16?
Yeah.
So each of these revisions to the CAMs, they have been simplifying them. CAM97 was like a mess initially, but ultimately, like perception of like a color appearance attribute is really an axiom. The OSA was in the 60s, they got together and they said, we cannot quantify with a distinct system human vision. We can't do it. It's not possible. This thing is non-Euclidean, we can't do it. But each of these systems that have followed, sometimes they get more complex, we're able to simplify some things, but what's happening is that with each revision, we're getting a little bit closer to the target. And so, there are some creative ways to reduce your computational expense by using lookup tables instead for pre-calculated values, which is something you can do when you have a set of static parameters. But I don't necessarily agree that they should be simplified. Let's make it more accurate at whatever cost that is. Let's hit the target.
I'm a designer and I also teach color, and I know that this assignment is one of the difficult ones for the students. And right now I'm looking at my Photoshop. I don't have CAM16. Where can I get CAM16?
So that's an excellent question, and my answer is 2 words: stay tuned. It doesn't exist yet. The CAM16 color picker. That's actually what I'm working on in my capstone this year. I want this color picker to be on the market by next spring.
And then let's say that we have this CAM16. Is it for the digital design, or could we also work for the manual one?
So that's a good question, and initially it would be for digital, but working in CAM16 actually would allow you to think in terms of both, because these measurements, I'm not sure if we're screen anymore, but I took these measurements from Albers' book, right, with the spectrophotometer. And so CAM16 is device independent. You're taking a set of tri-stimulus values, which could be anything that we're seeing, and we're giving it a color appearance attribute of this is how light it is. this is the chroma, this is the hue. And so even if, let's say, a color is not necessarily producible on an RGB display, like it would be your really vivid oranges is a good example. Like, you know, Accutane, like the orange on the Accutane packaging is 8. The chroma is like not producible. I tried. You can't do it on a screen. And so if they have these color appearance model like coordinates, even if they're not able to preview it on their screen or whatnot, people are getting used to actually understanding what like a chroma unit is, what is a lightness unit, how are these things ordered, what is this tool, that they can have, let's say, their gamut like description, have the thing knocked out, and they can have a little X that says this color is out of gamut, but it would be whatever that lightness is, just a little bit more chromatic. Like it has the potential to like include colors that can't be produced on screens.
Yes, actually you can use LAB in Photoshop. It's a kind of uniform color space, but not good enough.
So actually, let me say something about that LAB picker in Photoshop. So it's just LAB, and designers inherently for their tasks need LCH. And also the LAB picker in Photoshop does not mark out the gamut. I mean, you'll be I mean, it'll tell you if you go to like chroma like 120, then it's like not chroma A like 120, that something's up. But the color picker in Photoshop, like the lab, it just takes the gamut and it just kind of turns it into this weird gradient. And because there's no chroma or hue support, if let's say I just want to take that blue and just make it a little bit less like vivid, I'm having to like open Excel and like do the Euclidean distance formula to like produce the chroma.
That APP in the future. Okay. Any other comment? So let's think all